Okay, class, let's continue with our discussion on this particular chapter. And the focus of this chapter, as we discussed, is to be looking at more complicated structures of a control systems, meaning the input signals, we have output signals, and we have various feedback or feed-forward loops that make the connection a little bit more complicated. So this is the example we show earlier in our Tuesday's class. So we have the input, again the reference input on the left hand side is of our R signal, and we have our Y signal, the output on the right hand side. And we have a total of 7 subsystems within, so meaning the reference input will go through all the G blocks, and at a certain point some of the intermediate signals, for instance, after this G3 from this point will have a signal going this route, and then the eventual output Y will be fed to 2 separate loops, as we have seen in the previous example. Okay, and so on Tuesday we have looked at this system a little bit and figure out well, there are 3 loops, and there's one direct path from R to Y. So this is what we have calculated from the direct path gain. So we multiply all the transfer functions along this direction, along the direct path, and we calculate the gains of each loop. Of course, when we calculate a loop gain, we have to pay attention to what is the sign that will eventually come back to the main path, right? So we'll focus on whether or not this is a plus sign or minus sign. So this is plus sign, so that's why loop number 1 will turns out to be a positive number right here. Okay. And for the other cases, we have negative sign here or negative sign here. That's the reason why when we come back, we will have negative signs here and here. Okay. So these are some of the issues we have discussed. Now, on Tuesday, we also made a hypothesis that the transfer function of a complex structure, as we have seen, can be calculated as the ratio between the direct path gain, the numerator, to 1 minus the total loop gain, the denominators. So this class, through this example, will demonstrate whether or not this rule is true. Then we'll try to see how we can further make this applicable to other cases. So to do that, let's just maybe have a quick look. So I'll erase this to make this a little cleaner. So let's look at this graph, and let's talk a little bit about what about the signals involved. So this part is my output Y. Of course, in the frequency domain, it's going to be Y of S, right? Y of S. So I'll simply write Y to make sense simpler. Now, if this is Y, right? So that means in the 2 loops, I have Y here, and I have Y here. And of course, this will be H1 times Y. This will be H3 times Y coming back. And on the left hand side, of course, this is R of, so this will be R of S, my reference input. And then we can continue with all this discussion. So here will be our R minus H3Y. This is the error signal, sort of. This will be the input to the G1 block. Okay. And of course, here will be G1 times R minus H3Y. Okay. This is the output of the G1 block. Now, if we go backward, so this is how we go along the direction of the signal. And we can also go backward. For instance, if we look at this G4 block, okay, let's look at this G4 block here. If I know what Y is the output, right, then apparently the input here, the signal right here, should be what? Should be Y divided by G4. right? If the input is y over g4, then the output will be y divided by g4 times g4, that given is y. Right? So we know the input, we know the output signal, we know the transfer function, we can also figure out the output, the input to this. And if this is y over g4, so that means the input to H2 is y over g4, or the output of this H2 block will be H2y over g4. Now for this summing junction, now you know what happens on one side of it, and this is the other output. Of course, when we subtract the two, we can figure out what is the signal here will be G1 R minus H3 Y, and then minus H2Y. This will be the signal here, or the signal at the input of this G2 block. So this will be divided by G4. Okay. So we simply take the two input to this summing junction and one subtract the other. And of course, when this is done, since this one is also known, you just have to multiply everything by this G2. So I'll use another color. So this signal right here will be what? Will be G2 times this G1 R minus H3Y minus H2Y over G4. So that will be the input to the next summing junction. Right to here. Right here. So for this summing junction, again, we have one and we have the other. That means we also can figure out what is the signal to the input of G3. So this guy is also known, we can also write it out. I'll use a longer place, I need a little bit more space. So what is the signal right here? Okay. This is the sum of two signals, the sum of this one and this. So it will be G2 times G1 R minus H3Y minus H2Y over G4 and plus H1Y. Yes. Okay. So that will be the input to the G3 block now. Now, for the G3 block, this is the input. And the output we have calculated earlier, this Y over G4. Apparently, these two should be related by the transfer function. So that means if the output to G3 block, so let's say output of the G3 block is what we have figured out earlier, is Y over G4, sorry, to the G3 block. Yet it should be equal to the transfer function G3 times the input, which is what we have above, G2, G1, R minus H3Y minus H2Y over G4 and plus H1Y. So what I just did is I simply took, I simply took the input to the G3 block right? This is my G3 block. The input signal is right here. And I put it here. Right, so this is what I did. In the transfer function G3 as we have it, the output y over G4 is right here. This is how I calculated back in the backward direction from y to G4 and then to this y over G4. So if everything holds, this equation should be true. And now if I look at this equation, well, nice, I have y here, I have y here, y here and here. And also I have my reference input r. So I can separate the terms. And let's see how I can separate the terms. So first of all, what I want to do is I want to multiply G4 on both sides of the equation, so which will make this easier. So I'll multiply G4 here, I'll multiply G4 here. So we can cancel this on one side, and this eventually will cancel the G4 inside as well. So expanding this equation, I have y on the left hand side, and then G3 times G4, G3, G4 times G2, I can multiply this here. Yeah, so this will be G1, G2, R minus H3Y. Right? And minus G2 H2Y over G4. Right? And then plus H1Y. So I just distribute G2 with each of the terms inside. Now if I do one more step, I'll multiply G3, G4, distribute that to all the terms. I have y on the left hand side still. Now I have G1, G2, G3, G4, all four of them multiplied by r. So that's our first term. And then minus G3, G1, G2, G3, G4, H3y. Okay, so I'll be this for the second term. And then minus, again, so in this case G4 will cancel, so I have G2, G3, H2y. And then the last term, plus G3, G4, H1y. Next thing you do, you move all the terms with y to the left hand side and keep this r term on the right hand side. And it's not difficult to find out y will be equal to. I'll do a better job here. On top, you will have G1, G2, G3, and G4. So eventually multiply by r. On the left hand side, you start with 1y. And then you move this G1, G2, G3, G4. Maybe let me write it in a different form. So it'll be let me do this. Do 1 minus, okay, negative G1, G2, G3, G4, H3. So I want to keep this consistent with this 1 minus loop gain thing. So, and then in this case, of course, will be minus minus negative. I probably need a little bit longer here as well. So it'll be minus negative G2, G3, H2. And then minus, just in this case, G3, G4, and H1. Okay, times R. So this G1, G2, G3, G4, H3 has this Y. So I move the three terms right here all of them to the left hand side, eventually divide the coefficient to separate y from r. So this will be the transfer function. If I look at this final result, right, what we have is, if I ask for the transfer function, this is the transfer function you have. Okay, this will be the transfer function we have. Is this surprising? Now let's look at the numerator, G1, G2, G3, G4. See if I go up. What is it? G1, G2, G3, G4 is my direct path. Is my direct path gain. That checks out up here. And what about the other terms? Go down. First term here, minus G1, G2, G3, G4, H3. Do I have it? I have it right here. That's your loop gain of L3. This is L3. And minus G2, G3, H2. Do we have it? Minus G2, G3, H2. We have it here. This is my loop gain number 2. And G3, G4, H1. We have G3, G4, H1 here. I'm sorry, this is L2. And this is L number 1. So we have the 3 loop gain here, and this is my direct path gain. Okay. Now basically we prove that this rule, that the transfer function is equal to the direct path gain over 1 minus the total loop gain, still holds even for a slightly more complicated system. Now derivation procedure, right, by looking at the routing of the blocks and different, so we have to figure out where is the input signal, where is the output signal, right? We figure out all these intermediate signals here and there. This procedure is sometimes called the block diagram algebra, as I mentioned earlier, and this is exactly what we did in the simple case, right? In simple one loop feedback, classical feedback control structure, this is also what we did. We define the error signal E of S, how it can be represented by R and Y, and then we equate the transfer function, so Y will be equal to the 2 transfer function multiplied by my error signal, and then plug in my error signal right here to eventually find the transfer function. The way we calculate the transfer function of this more complex system is the same method, just more intermediate signals to figure out, right? We have to figure out almost every one of them, and sometimes requires a little backtracking from, backpedaling from the output transfer function to figure out how the input signal should be represented. And then eventually we put together the relationship right here, and then eventually we put things together to find the transfer function. Now, as you can see, basically, if I ask you to derive the transfer function of the system, you can use 2 methods. One is the complete procedure. Basically, let us summarize. So method number 1 is through what we call the block diagram algebra. Okay. This is through the intermediate signals. You need to figure out them and eventually equate both sides of the equation. Okay, this is what we did. And of course, it's also possible sometimes to rearrange the routings of the signals a little bit. Okay, reroute the routing of the signals a little bit, but this is what we call the block diagram algebra. It's usually more complicated. The other way that we usually do is what we call the Mason's law. Let me make it black. Your black. Maybe this will be. No, it doesn't. So let's see. Oh, maybe I made it too light. Maybe this will do the job. So the other way is through that formula, direct path and loop gain. This is the method that we have. So there we go. So method number 2 is through the formula. This is what we call the Mason's rule. Mason's rule. Okay, this is a new name apparently. So that tells you the transfer function is equal to your direct path over 1 minus the total of all the loop gains. Direct path, of course. Okay. So like what we have, so it's direct path gain divided by 1 minus the sum of all the loop gains. So 1 minus loop gain of number 1, 1 minus the loop gain of number 2, minus the loop gain of number 3, and so on. Now, it should be noted that although we have this Mason's rule, and in the homework and exam in all your applications in the future, feel free to use the Mason's rule directly. But this particular formula that we have here, so this particular formula, this is a simplified version of Mason's rule, of the actual Mason's rule. Okay. What should be the complete non-simplified version of Mason's rule, we'll discuss in the next video.